shearing stresses in the beams. We have started with this one, and one is we noted that the shearing stresses exist on a longitudinal plane in a beam due to bending moment, due to non-uniform bending of the beams. Now, what is the expression for determining this shearing stress that we had obtained? So this is what we came across, the expression tau equal to F A y bar upon I into B. Okay, what are these terms? F is the shear force at the section considered. A is the area of the section above the point at which you want to determine the shearing stresses. Y bar is the distance of centroid of this part of the area, that is the shaded part, which is above our point at which we are finding the shearing stress. So distance of the centroid of this area from our neutral axis, that is this y bar. In simple words, y bar is the distance of center of this area A from the neutral axis. So I is the moment of inertia of this entire section. B is the width of the section. So from this, I can obtain what are the shearing stresses in the beams, okay, at any point on the span and at any point within the cross section along the depth of the cross section. Okay, so we'll move on and see some of the cases about this shearing stress. Okay, that is, the first thing is we'll take up a rectangular section over here. So shearing stresses in a rectangular stress, how it varies and what is the maximum shearing stress. Let us try to look into this one. Okay, so first is for a rectangular section. So in this case, we'll look what is the value of shearing stress. So this is the section what we'll take here, right? And let's say the width of the section. Okay, so this is B, the width of the section, and D is the depth of the section, overall section. Depth is D over here, and the width is B. Okay, now position of neutral axis for this rectangular section will be at the mid depth, that is, it will coincide with our centroidal axis over here. So this is my neutral axis. So distance of this neutral axis is d by 2 from either sides. Okay, from top edge or from the bottom edge, the distance of neutral axis will be d by 2. For a straight section, neutral axis coincides with the centroidal axis. Okay, so this is my neutral layer or the neutral axis where the bending stresses will be zero. It will not experience any kind of bending over there. Okay, now to determine the shearing stress, let us take one section over here. This is the section at which we want to find the shearing stresses. Let us say this is xx and it is at a distance y from our neutral axis. So I want to know what is the shearing stress developed at this section, okay, at this point in this cross section at a distance y from the neutral axis. In this layer, what is my shearing stress over here? Okay, now it may be this cross section may be a simply supported beam, or it may be a part of a cantilever beam, any kind of beam. Okay, now when we determine shear force, okay, let us say this is having a shear force of F. Okay, so let the section be subjected to to a shear force F. Okay, so this shear force value F can be determined by knowing what is the loading on the beam. Okay, so that F may be somewhere, anywhere. It may be at the support, it may be at the midspan, over here, anywhere. Okay, so we can determine this shear force value F. For this purpose, we'll consider this value to be F over here. Okay, now the shearing stress. Okay, shearing stresses on a longitudinal plane at a distance on a longitudinal plane xx, okay, at a distance y from the neutral axis. We are going to find out what is the shearing stress on a longitudinal plane, okay, this plane xx, and it is at a distance y from the neutral axis. So that is expressed as tau, which is equal to f a into y bar divided by I into b. Okay, now for our section, for a rectangular section, what I have, I is equal to b d cube upon 12. Okay, now the next question is about this a and y bar. B is the width of the section. Okay, so I need to know what is the area, okay, of this shaded portion and distance of its centroid from our neutral axis. Distance of centroid of this shaded portion from the neutral axis. Let's say the centroid is here. Okay, so what is this depth here now? So this depth over here, which is here, depth of this shaded area, it will be d by 2 minus y. This distance will be d by 2 minus y. Okay, so d by 2 minus y. I hope that is clear how it is the depth of the shaded area, how we got that one. Okay, from the neutral axis, what we have considered, the section is at a distance y. Okay, and neutral axis position. Okay, it is d by 2 from the top edge. So this depth, okay, it will be d by 2. This d by 2 minus y. Okay, now what I want here is, what is this y bar? This will be my y bar, a and y bar for this shaded area. So this is y bar here. So that is what I need to determine for this, for finding the sharing stresses over here. Okay, so this is y bar. Now let us go with this. Now first is area of the shaded portion. So what is the area of the shaded portion? This is A, which will be equal to d by 2 minus y into b, b into d. Okay, b, width of the section. This is a rectangular section. B is the width. What is the depth? D by 2 minus y. So b into d by 2 minus y. This is my area. Okay, distance of centroid now. What is the distance of centroid? Distance of centroid of the shaded area from our neutral axis. What will happen to that? Or this y bar, Okay, we are actually calculating this y bar. So y bar will be equal to what? This y plus half of d by 2 minus y. Now this is a rectangular portion. Centroid will be exactly at mid depth. That is half of this depth. So it comes out to be y, okay, plus 1 by 2 into d by 2 minus y. Okay, so that is the position of our centroid of the shaded area measured from the neutral axis. Okay, now what this comes out, if you simplify this, it will give you y bar as half of d by 2 plus y. Okay, you can just open the brackets, y minus y by 2, it will become y minus y by 2, or finally this y bar, okay, it will be 1 by 2 into d by 2 plus this y. You can simplify this, try opening that bracket, and if you do the simplification you will get that one term. Okay, now I can substitute those terms in this equation. Therefore the shearing stresses, okay, what I need to determine is these shearing stresses. The shearing stresses tau will be equal to F, the shear force at the section, into A, which is into B into d by 2 minus y. This was our area, into y bar. What is y bar? 1 by 2 into d by 2 plus y over here. Okay, whole thing divided by b d cube by 12 I into b. B is the width of the section, into b. Okay, so this we can simplify further here. Okay, what it gives me when I simplify this, this is a into y bar term entirely, this is a into y bar, f into f a y bar divided by I into b. That is what I have used here. So on simplifying, you'll get it as f into b by 2, okay, into, in the bracket, d square by 4 minus, this will be y square, okay, this is a minus b, a plus b, a square minus b square, okay, and this entire thing divided by b d cube by 12 I into b. Okay, further if I cancel out the terms, b and b will be gone, this 2 and this will become 6, okay, or it gives me 6 f, okay, into d square by 4 minus y square divided by b into d cube. Okay, this is our shear stress at any distance y from the neutral axis in a rectangular section. Okay, so one is it varies parabolically, first thing, because here variable is y, so y is having a power 2, y raised to 2. It varies parabolically. Along the depth of the section. So along the depth of the section, the variation is parabolic. Now next thing is at y is equal to 0. If I take the top, this neutral axis at that point, what is the shearing stress? And when y is equal to d by 2 at the top edge or at the bottom edge, what will happen to the shearing stress? Okay, so at these 2 points, let us evaluate what will be the shearing stress here. Okay, so first is at edges, It may be top edge or the bottom edge. At edges, y will be equal to d by 2. So when I substitute y equal to d by 2 in this equation, what happens to this shearing stress? Tau becomes 0. Y square d by 2 whole square, that is d square by 4. This will become, this term will become 0. So tau is 0. And at the neutral axis, what happens here? At the neutral axis, y is 0. The value of y is 0 because this y has been measured from the neutral axis. So when I am at the neutral axis, the value of y is 0. So what is happening to the shearing stress now? So now tau will be equal to, this y is 0. So it comes out to be, how much it will be? 6 f d square and d, okay? 6 f upon b into d. It comes out as 6 f upon b into d by 4, okay? Or if I reduce that, it will be 3 by 2 f upon b into d. Or even I can put it as tau is equal to 3 by 2 into f upon a. B into a, d is nothing but area of our rectangle, okay? So f by a itself is representing the shearing stress on a transverse plane, okay? So that is the shearing stress on a transverse plane. So we call it as the average shear stress, f by a. So f upon a, okay? So that f by a is nothing but the average shear stress. So what I can say is the shear stress at the neutral axis is 1.5 times the average shear stress, okay? So this can be concluded over here. At the neutral axis, what we have, the shearing stress, it will be 1.5 times the average shear stress. What is average shear stress? Average shear stress is the shear stress which is acting on this transverse plane, okay? Which can be obtained by dividing the shear force value by the area, cross-sectional area. So this shear force value divided by cross-sectional area is our average shear stress. We call it as average shear stress, okay? Right, let me take it over here. F by A is nothing but the average shear stress on the section. I can call it as tau average. Therefore, the shear stress at the neutral axis is equal to 1.5 times the average shear stress. If you know average shear stress, you'll be able to tell what is the shear stress at the neutral axis. It will be 1.5 times the average shear stress. Okay. Now, if you plot the variation, the one more thing I want to make it here is how the variation is. So what we have noted here is at the two edges, okay, the shearing stresses are 0. Okay. At the two edges, the shearing stresses are 0, and at the neutral axis, we have the shearing stresses as 3 by 2 times the average shear stress. Okay, so the variation would be something like this. It varies parabolically. That is one thing what we have noted. So the parabolic variation would be something like this. So this is the shearing stress variation. It will be perfect parabolic. Okay. I just show that some good example, but it varies. this parabolically at this point of time. Keep that in mind. It will be something like this. This is at the neutral axis, exactly at the neutral axis. So that is the variation of shear stress. Okay, so you require two terms over there whenever you want to find out that A and Y bar. Shear force has to be determined from the beam. Okay, knowing the reaction and the loading on the beam, the shear force value has to be determined, and you require the cross-sectional properties I, and also the area of the section above the point at which you are finding the shear stress, and its distance of its centroid from the measured from the neutral axis. Okay, now next one, let us take up one more, that is triangular section. So let us take for a triangular section how the shear stresses vary and what will be the value of the shear stress at some important points over here. Like this is the triangle what we have. Okay, and let us say fine. Okay, B is the width at the base and H is the height of the triangle. So I, now in this case, that is the moment of inertia, what I require is about its centroidal axis, okay, which will be BH cube upon 36. I value for a triangle, moment of inertia value for a triangle about its centroidal axis will be BH cube by 36. Okay, so this is my centroidal axis as well as the neutral axis over here, what I have. So that is the centroidal axis and the neutral axis. So I'll take this centroidal axis here. So distance of this centroidal axis, what I have, so it will be at a distance of, first let me put these dimensions of the triangle. This base width is B, okay, and this height of the triangle, it will be H. We'll take that to be H over here. Okay, this is the height of the triangle, H. Okay, so this is the neutral axis, what I have marked here. Neutral axis. Now what we'll do is we'll consider a section XX somewhere over here. So for finding the shearing stress, one thing what you have to do is you should be knowing the point at which you need to find the shearing stress. Okay, so this is my section XX. Okay, so this is where I want to know the shearing stress in this section XX, and let me take this distance as y, measured from the apex of the triangle, this as a distance y here. Okay, so for this area, I want to know now what is this area of the shaded portion and distance of its centroid measured from the neutral axis, that will be our y bar term over here. So these two have to be determined. Okay, so first thing, distance of centroid or the width here. Again, let F be the shear force so F is the shear force at the section within the beam, okay, and area of this shaded portion. First thing is I require the area of the shaded portion here. So it will be half of this height into base, half height into base. What is this base here? So it will be b by h into y. Okay. So that is, if you use the similar triangle, if you take it as b1, okay, will be equal to b by h into y here. Okay. Therefore, area A of the shaded portion will be half, okay, base, okay, that is b by h into y into the height y. Okay. So what it gives us, the area will be b by 2h into y square. Okay. Distance of centroid now. Distance of centroid of the shaded area from the neutral axis. We have taken it as y bar. Okay. Now how much will be that y bar here? So I need to calculate that y bar. Okay. So what we have is measured from this apex. Okay. This y bar will be 2/3 of y. Okay. And what is this distance of neutral axis measured from the apex? So that will be 2/3 of h. These are all properties of the triangle, what I am writing here. Centroidal distance of the triangle measured from the apex. Okay. So neutral axis is coinciding with centroidal axis of the triangle. So it is 2/3 of h measured from this top edge apex. Okay. Similarly, for this smaller triangle, it is 2/3 of y. So if I find this difference between these two, that itself is my y bar term here. Okay. So y bar from the figure, what I can write is it will be equal to 2 by 3 h minus 2 by 3 y. Okay. 2/3 of h minus 2/3 of y. So that will be my y bar, centroidal distance of the shaded area measured from the neutral axis. Okay. Now what about moment of inertia? Moment of inertia of the triangle about its centroidal axis or neutral axis. Both are same in our case. So it will be I, which is equal to bh cube upon 36 here. Okay. So now if I substitute all these a, y bar and I in the expression for shearing stress, I'll get to know what is the shearing stress over here. So therefore shearing stress is tau. So what will happen to tau now? It will be equal to f a y bar divided by I into b. Okay. So this will be f as it is b into y square upon 2h. Okay. Y bar 2h by 3 minus 2y by 3 f a y bar. Okay. This whole thing divided by b h cube by 36 I into base b. Sorry, b, that is at the section. What I have, the section is not having the same base, so it is b by h into y. With that section, what we have considered, b by h into y over here. Okay. For a rectangle, it will remain constant, but for a triangle, the width will vary. When I come to this section, at this point, what is the base width b? Okay, that has to be substituted. It will be b by h into y. Okay, so if I simplify this, so will be equal to, so this will be now cancelling out these terms, y, okay, 2, 2, okay, 3, 6. So it comes out as 24 into f. Can you simplify this along with me? Please simplify this. Okay, 1b is gone, h is gone, and 2 by 3, 2 by 3, if I cancel out, it will be 1 by 3. Let me first simplify this term, top one. So it will be h minus y will be remaining there. F b. So 36 by 3. 2 and 2 is cancelled, 1 by 3. So if I take it out, I'll have 36 by 3 into f by b into h. Okay, into, I have the y term, one y term on the numerator, into here it will be h minus y. Okay, please tell me you'll get it this much or not, or this comes out as, can you give me the value division, what happens to this? Happy so so I'll be having this 12, okay, 12 f by b into h into y into h minus y. Okay, so here also we have the y square term. If I multiply this y within this, we'll come across y square term. So here the shearing stress is also varying parabolically with the along the section. Okay, so further what I can do is this b into h. Okay, I can express it in terms of average shear stress. Okay, area of the triangle will be half base into height. Okay, so for that purpose I can take it as 24 times, okay, f upon, okay, this is b h cube, right. So you should be able to come with this particular expression. Tau is equal to 24 times 24 f upon bh cube into y minus y into h minus y. Okay, this also varies parabolically here. I want someone to check this simplification. What is done here? Take this term, this one, okay, and try simplifying that. Please tell me whether what we got is right. So I have written tau as 24 times F upon BH cube into Y into H minus Y. Okay, now let us consider 2 points. One is at top edge. So at top edge over here, Y is 0 at the top edge, at the apex. At the top edge or at apex, Y is equal to 0. Therefore, shear stress tau is equal to 0. That is one thing. Second one, at neutral axis, what is happening to the Y value? Not at the neutral axis, at the bottom edge. We'll come to this neutral axis later. Y will be at bottom edge. Okay. At the bottom edge, Y will be equal to H. Y comes out to be equal to H. So what happens to that? Again, H minus Y term is there. So we should have please go through that. I'll share that derivation later and after doing that. So what I have is, let me take that expression what we came across. Tau is equal to 24 F upon BH cube into Y into H minus Y. Okay, so one is at top edge, Y is equal to 0, and that gives us tau is equal to 0. At bottom edge, Y is equal to H, so this term will be 0, therefore tau is equal to 0. What about maximum shear stress? So for maximum shear stress, you should have d tau upon dy is equal to 0. You should differentiate this equation with respect to y once and equate it to 0. So if I differentiate that, what happens is 24 F upon BH cube. So it will be H, okay, H into Y, differentiation of H into Y, H minus differentiation of Y square will be minus 2Y. So this should be equal to 0. Or what it tells me, this H minus Y term has to be 0. This cannot be 0 here. So Y will be equal to H by 2. This is a point where maximum shear stress will come. Y equal to H by 2, not H by 2. How much it will be? So maximum shear stress. Okay, yes. Differentiation, correct. Y equal to H by 2. Or when I use that Y equal to H by 2 in my equation, tau max, I'll get tau max. So that is equal to 24 plus 24 F upon BH cube into H by 2 into H minus H by 2. All this tau max will be equal to h by 2 h square by 4, or h square, h is gone, 4, that will be 3f upon b into h. Okay, 3f upon b into h. Please see this simplification of 3, 6. Okay, this will be 6f upon b into h. 6 4s up, this is 24, 4 6. Okay, or 3f upon half b into h. So this is tau max 1 by 2 b into h is nothing but it is the area of the triangle. So will be 3 into f by a, or tau max, maximum shear stress, will be equal to 3 times the average shear stress. 3 times the average shear stress. So that is what is there for the triangular section. And one more is at neutral layer, at neutral axis, y is equal to 2 by 3h. Therefore, what will happen to the shearing stress? Tau is equal to 24 f upon bh cube, okay, into this 2 by 3h into h minus 2 by 3h, or this tau at the neutral axis will be equal to, if you simplify that, it will give you 4 by 3 into f by a, or at the neutral axis it will be 4 by 3 times the average shear stress. Okay, try simplifying the two equation what I told you. This actually comes out. Try that simplification. So you should be able to come up with this values. Okay. For the derivation, you just go through this video again. I would have saved that one in between. So I lost that derivation what is done. Okay. I'll share that derivation later. Okay, so these are some cases: triangular section and rectangular section. What we came across here is how we can determine the shearing stress at any point within these sections, or for any given section, and what is the variation of shearing stress across the depth of the section. So we are seeing in these two cases it is varying parabolically, and also at some points at the neutral axis, at the top edge, at the bottom edge, we have determined the shearing stress, and also we have related that with the average shear stress. Average shear stress will be the shear force at the section. Okay, shear force at the section divided by the area of the cross section. That will be the average shear stress what we have. Okay.